In our last lecture, we explored the issue of internal symmetries and exactly what consequence they have on the scattering matrix. We saw that in the case of internal symmetries, where momenta or spin of particles are not affected, but only their particle species labels are, the operator u of t, which implements a particular transformation capital T on the Hilbert space of in and out states, happens to be the same as u0t. That is, the operator which does the job on in and out states happens to coincide with the operator which does the job on free particle states. And just like in all other cases of symmetry, we end up with the statement that u naught t commutes with the scattering operator, and because u naught t is the same as u of t, we end up with the result that u of t commutes with S. Now, the particular internal symmetry operation that we are going to talk about as a continuation of an unfinished discussion in the last lecture is isospin symmetry. In isospin symmetry, basically you have a 3-parameter group, and for infinitesimal values of these parameters, theta 1, theta 2, theta 3, u of t of theta is identity plus I t1 theta 1 plus t2 theta 2 plus t3 theta 3, where t1, t2, t3 are the 3 generators of isospin symmetry, and they happen to obey exactly the same commutation relation as the more familiar angular momentum operators do. In fact, that is the reason why this is called isospin. It's like spin in a sense. We discussed the fact that isospin symmetry is not an exact symmetry of the real world. The Hamiltonian for the strong interaction commutes with T1, T2, T3, our generators of isospin. Hence, S actually commutes with T1, T2, T3 if you only have strong interactions. Electromagnetism does not respect isospin symmetry. We saw that as a consequence of isospin symmetry, we will have particle multiplets. That is, just like you have multiplets in angular momentum, with a particular angular momentum quantum number j corresponding to 2j plus 1 states, here you will have a multiplet characterized by capital T, basically the equivalent thing for isospin. T square's eigenvalue is given by capital T into capital T plus 1, and within that multiplet you will have 2t plus 1 states characterized by the T3 eigenvalue. And these states will essentially be different particles, but if strong interactions were all we had to worry about, they would essentially behave like states of the same superparticle. And you expect them to be nearly identical in their masses. They would have been exactly identical in masses and many other properties if isospin were an exact symmetry. But because isospin symmetry is only approximately obeyed, you find that the particles are very close to each other in behavior, but not exactly the same. Now, one of the points that we raised at the end of the last lecture was exactly what consequence isospin symmetry has on two-body scattering processes, a process in which a particle A interacts with a particle B, and what comes out are particles C and D. C and D may be the same particles as A and B, in which case we call this an elastic scattering, but there could be entirely different particles produced as a result of the interaction. And what we saw is that the demand that u of t commutes with S actually leads to this particular restriction on the S matrix elements. When I have written the S matrix elements here, you have the outgoing states on this side, the states corresponding to the particles C and D, and you have the in-state labels on this side, corresponding to particles A and B. And of course, these particles are characterized by more than just their isospin third component, which essentially talks about the identity of the particles. The moment of the particles, their helicity states are all important, but they are being suppressed in this notation here. We are focusing on what is relevant as far as isospin is concerned. It turns out that we can write down a formula for the scattering matrix element entirely in terms of Clebsch-Gordon coefficients, these numbers here, and a so-called reduced scattering matrix element ST, where ST is independent of the individual third components of isospin. It just depends on the total isospin quantum number, and the sum here is over all capital T and T3. Now ST also depends on other parameters like the momenta and helicity states of the particles. That's, as I have said, being suppressed in this notation. Now let me remind you that the Clebsch-Gordon coefficients that you see here are basically coefficients of these eigenstates of T1 square, T1's third component, T2 square, and T2's third component. In the expansion, in the eigenstates of T1 square, T2 square, capital T and T3. So this is a notation which is often used in quantum mechanics texts. We have just used a slightly shorter notation here. T1 and T2, the total spin angular momenta, in this case the isospin angular momenta of both the particles is common on both sides here. So we have just put them here as a single label. Now, one thing is very important. Although we are claiming that capital T and T3 is to be summed over, which may make this right hand side look like a pretty formidable expression, it's actually not really a very large number of terms that you have to sum over. Because of the property of the Clebsch-Gordon coefficient, they will vanish unless T3 equals the sum of these two T3 values. So T3 actually has only one value here, so there's only one term in the sum for T3. T3 takes the value Ta3 plus Tb3, and that in fact has to be equal to Tc3 plus Td3. This is a conservation law, which, as I have mentioned before, is not really a surprise given the fact that T3 is related to the charge and hypercharge of a multiplet, and the fact that charge is conserved and hypercharge, baryon number plus strangeness, is conserved too. The fact that this is a conserved quantity does not really come as a surprise. As far as the capital T sum goes, note that this particular Clebsch-Gordon coefficient will vanish unless capital T is somewhere between capital TA plus capital TB and the difference of capital TA and TB. A similar thing can be stated about this. So basically this sum over capital T only runs over capital T's which satisfy this restriction. It goes from the larger of the two values of TC difference TD and TA difference TB, and the smaller of the two values TA plus TB and TC plus TD. Any value of capital T beyond that, either this factor or this factor will vanish, so there will be no contribution to the sum whatsoever. For a given particular situation, it might turn out that there are only very small number of capital T values to worry about. So the right hand side of this expression could be a sum of a small number of terms. Now I'm pretty sure you're all pretty familiar with Clebsch-Gordon coefficients from angular momentum theory in quantum mechanics. In case you have forgotten, let me just give you a quick reminder here. Capital T vector here is a sum of T1 and T2, two individual isospin vectors. Of course, this means capital T's one component is equal to T1's one component plus T2's one component and so on. And these states, the states which I have written with a round bracket and labeled T1, T2, T3, are simultaneous eigenstates of T1 square, T2 square, T square and T3, where T3 is T1 3 plus T2 3. And these states, on the other hand, the ones with a angular bracket, the standard notation for the ket, are ones which are eigenstates of T1 square, T2 square, T1 3 and T2 3. It just so happens that the operators T1 square, T2 square, T1, 3, T2, 3 form a complete set of commuting observables, and T1 square, T2 square, T square and T3 forms a different complete set of commuting observables. So you can have simultaneous eigenstates for these four operators, or you can have simultaneous eigenstates of these four operators. And since we are talking about the same space here, these simultaneous eigenstates can be expanded in terms of each other. In particular, if you were to try to expand these states in terms of these ones, the coefficients will come out to be the Clebsch-Gordon coefficients. Of course, if you were to try to expand these states in terms of these, that can also be done. The corresponding coefficients should come out to be complex conjugates because they are the overlaps in the wrong direction. But it can be shown that we can always choose our phases of states in such a way that the Clebsch-Gordon coefficients turn out to be real. So no matter whether you're talking of overlaps of the round bracket kets with these kets or the other way around, you get the same number basically. Complex conjugation of a real number, of course, does not change it. Now, this is essentially something we have already covered in the last lecture. Weinberg does not go any further than this, simply because Weinberg's assumption is that this is well known, and moreover, this is really the domain of specific interactions, something an elementary particle physics text would really be interested in. Weinberg's book, of course, discusses about the bigger picture of quantum field theory in general and does not want to get bogged down into the nitty-gritty details of specifics like this. However, I do feel that this result, this particular formula for the scattering matrix element, is actually quite useful and should really be discussed further. So I will do two things in today's lecture. One is I will prove this result for you, and the second one is I will discuss some applications from elementary particle physics. So first, let's take a look at the proof. To prove this result, we will start from the fact that for a system with isospin symmetry, the transformation u of t of theta, which is carried out on the in and out states, or also in this case, the same transformation is carried out on the free particle states, to implement an isospin transformation, commutes with S, no matter what value of parameters theta 1, theta 2 and theta 3 you use. In particular, if you use infinitesimal values for these parameters, then u of t of theta becomes this. And this has to commute with the S operator. A consequence immediately is that for all of j, 1, 2 and 3, tj hat commutes with S. Now notice that I have used a hat on top of the isospin operators, whereas I have not used a hat to indicate either the fact that u or s are operators. The reason for that is pretty simple. I would really like not to have to bother writing hats. However, as far as isospin is concerned, especially in this lecture, I will have to talk about isospin operator and their corresponding eigenvalues. And very often, the isospin operator and the eigenvalue has the same notation. So we just use a hat to distinguish whether we are talking of T3 hat, the operator, or T3, the eigenvalue. Now, having clarified the reason behind hats on top of TJs and not on S, let's go on to see its consequences. An immediate consequence, of course, is T3 commutes with S. So do T plus minus and T square. And T plus minus here are the so-called raising or lowering operators for isospin. These are exact analogues of similar operators for angular momentum, defined by T1 plus minus IT2. And T square is T1 square plus T2 square plus T3 square. Given the fact that T1, T2 and T3 individually commute with S, these commutation relations are trivial. Now let's take a look at the consequence of the fact that T square commutes with S. We start with T square commutative with S being 0, then apply that operator on a state phi, which is characterized by the TATB eigenvalues for TA square and TB square the operators. Of course, TA and TB are not the eigenvalues. TA into TA plus 1 and TB into TB plus 1 are, but we are going to usually not bother with the difference and say TA and TB are T square eigenvalues. Similarly, T here is in the same sense a capital T square eigenvalue, and T3 is of course a small t hat 3 eigenvalue, where t hat 3 is the total isospin angular momentum's third component. So we apply this t square comma s commutator on this particular state and take the inner product with a similar state, in this case with t prime, t3 prime. These are of course eigenvalues for t square and t3 again, and tc, td eigenvalues for tc square and td square. Then this of course has to vanish, simply because t square commutes with s. But rewriting t square's commutator with s as t hat square minus s t hat square, applying t hat square on the right on phi t, t3, ta, tb, and here this t hat square on the left on phi t prime, t3 prime, tc, td, what we see is that this relation immediately follows. The matrix element of S between these two states times this quantity happens to be 0. And what this implies is, unless capital T equals capital T prime, unless you have the same total isospin angular momentum quantum number on both sides here, this matrix element must vanish. A very similar thing can be done with the fact that T3 commutes with S, and that will immediately lead to the result that this matrix element will also vanish unless T3 equals T3 prime. So although we could be interested in general matrix elements like this, but frankly, the only ones which will be non-zero are the cases where T prime and T are the same and T3 prime and T3 are the same. So let's focus on that. Now, the next thing that we will do is apply the result that T minus commutes with S and try to talk about what this predicts for the matrix element of S between states. Notice that I am still not using T3 to be the same on both sides, simply because the effect of T minus will be to change the T3 eigenvalue. Indeed, if we write this as T hat minus S minus S T hat minus, apply T hat minus on this using the standard rules for angular momentum algebra. Remember, isospin algebra is the same as angular momentum algebra in that respect. It will lower the eigenvalue for T3 to T3 minus 1. On the other hand, T minus acting on this essentially means that you are applying the adjoint of this, T minus dagger, that is T plus on this, will raise T3 prime's eigenvalue to T3 prime plus 1. So this will give you these two terms. One in which T3 prime gets raised to T3 prime plus 1 by the action of T minus, basically the action of its adjoint T plus on this side, and the other in which T3 prime stays the same, but T3 gets changed to T3 minus 1 because of the action of T minus. The factors in front here are the standard factors that you get, which should be pretty familiar from angular momentum algebra. Now, notice that this equation is trivially satisfied unless T3 prime plus 1 is equal to T3, because unless that happened, both of these factors would vanish, and so you will get 0 equal to 0. But if you use the non-trivial case, that is, use T3 prime plus 1 is T3, which is the same as T3 prime is T3 minus 1. So, both of these factors can be non-zero at the same time. You end up with this result. These two P factors, under the condition T3 prime equals T3 minus 1, become exactly equal. Notice that this factor then becomes T minus T3 plus 1, the same as this one, and this factor essentially becomes T plus small t3, which is this one. So these two factors then cancel out, and you are left with the fact that these two matrix elements, this one where T3 prime plus 1 has been replaced by T3, and this one where you have replaced T3 prime by T3 minus 1, are actually equal to each other. Here you have a situation where all the other quantum numbers are unchanged, but T3 has changed to T3 minus 1, yet the value of this matrix element has not changed. In other words, the matrix element turns out to be independent of T3. So within a particular multiplet, it depends only on capital T, it does not depend on T3 at all. This is what we have called ST. Let me emphasize once again, ST still depends on the other parameters which are not really mentioned in this notation. After all, the isospin angular momentum is not the only parameter to worry about. You do have momenta and spin of the particles. ST will depend on all of them, but will not depend on T3 in particular. This actually is nothing but an application of the Wigner Eckart theorem for the special case where S is a scalar operator, an operator which does not transform under the kind of transformation you are carrying out here. S being scalar is directly related to the fact that U of t, the transformation operator, commutes with S, and therefore the changed S, U inverse t S ut, is the same as S. From this point, there's really only one thing left to be done. Our scattering matrix element S Tc3, Td3, Ta3, Tb3 is actually not this matrix element. It is the matrix element of S between the states which are characterized by well-defined eigenvalues for Ta square, Tb square and T hat A 3 and T hat B 3, as well as on this side Tc square, Td square, T hat C3, T hat D3. These are not those eigenstates. These are eigenstates of different operators, a different complete set of commuting observables. But you know how to relate them, and an easy way to do that would be just to insert the identity, the sum over all capital T and T3 of this structure. Essentially is the identity operator, and on this side you also do the same thing. Another identity operator goes in. And now you notice that what this has allowed you to do is rewrite our S matrix expression in terms of the matrix elements that we have just shown is independent of T3 times these coefficients. And these coefficients are nothing but the Clebsch-Gordon coefficients relevant for the cases. And this is how you land up with the result. This particular thing is this Clebsch-Gordon coefficient, and this factor is this Clebsch-Gordon coefficient. And of course, in the middle you have this particular result, which is ST. Now, of course, you have a sum over T and T3 and a sum over T prime and T3 prime. But remember, these matrix elements, the matrix elements here, will vanish unless T equals T prime and T3 equals T3 prime. So the double sum over both T, T3 and T prime, T3 prime becomes a single sum over only capital T and T3. And the same T, T3 values are used on both of these. So this is the proof of the result that Weinberg quotes at the end of his section on internal symmetries. Now that we have a proof of this theorem, let us take a look at what its possible applications could be. Of course, this is only applicable to two-body processes, so let's consider a specific two-body scattering process. Well, actually, instead of considering one two-body scattering process, let's consider two. One in which a proton collides with a proton to produce a deuteron and a pi plus, another in which a proton collides with a neutron to produce a deuteron with a pi 0. Of course, both these processes conserve baryon number. P and P have a total baryon number of 2. The deuteron, a p and n bound state, has a baryon number of 2. Lepton number conservation is trivial. There are no leptons on both sides of these equations. Charge conservation is clearly satisfied. In the process marked A, the net charge on the left hand side, incoming side, is 2, and the net charge on the outgoing side is plus 2 again, both deuteron and pi plus being positively charged. In the process marked B, the net charge in the incoming states is plus 1, 1 for the proton, 0 for the neutron. The net charge is plus 1. Also, again for the deuteron plus pi 0, the charge coming from the deuteron. Let us now take a look at exactly what isospin symmetry has to say about the relationship between the two scatterings. To begin the discussion, we must assign an isospin to the deuteron. Now, the deuteron is a Pn bound state. So, from ordinary angular momentum algebra which we adapt to isospin, we know that it can be either a antisymmetric bound state like this or a symmetric bound state like this. In terms of isospin, these are of course half-half states, and this will be an isospin singlet. This, on the other hand, would be a zero term of an isospin triplet. Now, which one of them actually represents a deuteron? Note that if the deuteron had been this state, the state with capital T equal to 1, T3 equal to 0, then we would have observed the 1, 1 state and 1, minus 1 states also. Isospin symmetry would have ensured that whatever binding strength this state has, 1, 1 and 1, minus 1 would have essentially the same binding strength as far as the strong interactions are concerned. And of course, the strong interactions are the dominant term as far as binding energy is concerned. So, if deuteron had been 1, 0, we would also have observed a proton-proton bound state and a neutron-neutron bound state. We don't see any such thing in nature, and this forces us to conclude that the deuteron is not one term in a triplet, but rather the other possibility, that is, a term in the singlet. So it must correspond to capital T equal to 0 and T3 equal to 0. So now let us take a look at the scattering matrix element for the pp to d pi plus process. So this process in which pp is the incoming state and d pi plus is the outgoing state. For that, the formula that we had discussed tells you that you have to sum over t the c values. Note that what you had here was c, tc, td. Then you had capital T, T3, TC3, TD3 for this Clebsch-Gordon coefficient. Then you had another Clebsch-Gordon coefficient which was TA, TB, capital T, T3, TA is third component, TB is third component. And then of course you had ST. And you have to sum this over capital T and T3 with the T3 sum being trivial. So here, notice that the input values that we have, TA3, TB3 are the third component of the isospin angular momentum for the input state which are both protons. So, protons correspond to capital T equal to half and T3 equal to half. So, half here, another half here. Of course, this means that the only T3 value that will contribute is 1, which is the same in both cases. On the other hand, for d pi plus, you have capital T of 0, T3 of 0. And for pi plus, you have capital T of 1, T3 of 1. Pi plus, remember, is the highest element in a triplet formed by pi plus, pi 0 and pi minus. Now notice that here the only possible value which capital T can take and still give you non-zero values for this is bounded by the maximum of the differences here, the difference in this case being 1 and difference here being 0. So, capital T must be greater than or equal to 1 for this Clebsch-Gordon coefficient to be non-zero. It has to be less than equal to 1 for both of these Clebsch-Gordon coefficients to be non-zero. So, the only possible T value is 1. And it's very easy to see that if you use a T value of 1, both of these Clebsch-Gordon coefficients become 1. So, you have just S1, that's a T, and a product of 1 times 1 in front. So, this particular scattering matrix element is simply S1. What about the other scattering matrix element? Scattering matrix element for proton and a neutron going to d pi 0. The thing is very similar, except that here you have a neutron label. So, the T3 eigenvalue for that particle changes to minus half. Everything else, well, almost everything else is the same. You have to have pion with zero charge here. So, 0 T3 eigenvalue. The rest, the multiplet structures are of course the same. So, both of them belong to capital T of half and half for the proton and the neutron. And here you had deuteron with 0 and pion with 1. So now when you calculate this, once again you will see that there is only one term that will contribute. That is capital T equal to 1. Now it's trivial to see that this one, which involves an addition with 0 angular momentum, will always have a Clebsch-Gordon coefficient of 1 if it is non-zero. So this contributes 1. This one on the other hand takes a bit more work. Note that this particular Clebsch-Gordon coefficient is actually the coefficient of half minus half, half minus half, this ket in the expansions of 1, that's for the T, 1, 0, and the two T square values, half and half for this. And you can easily see from this expansion, which should be a pretty familiar result in isospin theory or angular momentum theory, that this coefficient is 1 by root 2. So you have this particular scattering matrix element, the one where proton scatters to deuteron pi plus has S1, and the proton neutron scattering to deuteron pi 0 has a scattering matrix element of S1 by root 2. S1 of course is a reduced matrix element corresponding to capital T equal to 1. The ratio of these two scattering matrix elements is 1 by root 2, provided all the other things like the moment of the particles and their spin states stay the same. Now, to proceed further, what we will need to do is borrow a result from a coming lecture, which is a relationship between the scattering matrix elements and a more observable quantity, the so-called scattering cross-section. The scattering cross-section essentially tells you how many events will be detected by a detector. We will have more to talk about that later. But for the timing, let me just make a beginning by saying that a scattering cross-section turns out to be proportional to the modulus square of the scattering matrix element. So since the scattering matrix elements for the proton-proton to deuteron pi plus scattering is root 2 times the scattering matrix element of the proton-neutron to deuteron pi 0 scattering, it turns out that the scattering cross-sections are in the ratio 2:1, which means that a proton-proton scattering event will be observed twice as often as a proton-neutron scattering event, provided of course all the other parameters like the moment of the particles stay in the same range. And this happens to be something you can experimentally verify, and it turns out that this result does match with experimental observations, thus providing very strong proof that isospin is really conserved for strong interactions. Let us take a look at a slightly more involved application of the same basic idea. This time we are going to apply the idea to pion nucleon scattering, and we are going to consider three separate scattering processes. One in which a proton collides with a pi plus to produce a pi plus and a proton. This is an elastic scattering in which the identity of the particles is not changed. The second process is also another elastic scattering in which a proton collides with a pi minus to produce the same two particles again. And finally, you have an inelastic scattering in which a proton collides with a pi minus to produce a pi 0 and a neutron. Now, the pion and the nucleons used here are examples of isospin multiplets. We discussed this in the last lecture. The pion in particular is a member of an isospin 1 multiplet with pi plus, pi 0, pi minus corresponding to T3 values of 1, 0 and minus 1 respectively. On the other hand, the nucleon is part of a isospin doublet corresponding to capital T equal to half. T3 value of plus half corresponds to the proton, minus half corresponds to the neutron. Let us now take a look at the Clebsch-Gordon coefficients we will need for the subsequent calculation. Note that we are adding a T equal to 1 state with a T equal to half state. the pion with a nucleon, and therefore the possible total isospin angular momentum quantum numbers are t equal to 3 by 2 and t equal to half respectively. And if you look at the T3 eigenvalues, for this particular incoming state, the T3 eigenvalue is 3 by 2, 1 from pi plus, half from the proton. So this particular state actually corresponds to a situation where you are adding 1 and a half, the t equal to 1 and the t equal to half, and ending up with 3 by 2, 3 by 2. The other possible t value, that of half, is simply not possible in this case, because if capital T were half, you would not be able to get a small t3 of 3 by 2. The only way you can get this state, starting from states of pions and protons, or other pions and nucleons, is actually going to be this one. 1, 1, half, half. It's elementary angular momentum theory which tells you that this is the only possibility here. Even if you have forgotten that, it's pretty easy to see why this has to be true, because the only way you can get 3 by 2 is by adding up 1 with a half. That's the maximum possible isospin projections that the pion and the nucleon will have. So in this particular case, the relevant Clebsch-Gordon coefficient is simply 1. For the other two processes, the ones in B and C here, the in state is pi minus p, and this corresponds to a total T3 eigenvalue of minus 1 plus half, that is minus half. And so we need to really worry about two states overall, which is capital T of 3 by 2 and T3 of minus half, and the other one is capital T of 1 by 2 and T3 of minus half. So let us take a look at the corresponding Clebsch-Gordon coefficients for this case. To figure that out, we will start by using elementary quantum mechanical methods for calculation of Clebsch-Gordon coefficients. But instead of starting from the highest wave state, which is the usual approach, we will start from the lowest wave state. 1 half 3 by 2 minus 3 by 2. Now the only way you can get minus 3 by 2 as T3 is by having minus 1 from capital T equal to 1 and minus half from capital T equal to half. And so this is the only possibility with a coefficient of 1. This is exactly the same argument that we used here, except for the fact that we are using this for the lowest weight state. That means that the Clebsch-Gordon coefficient relevant here is going to be 1, but that is not really my interest. My interest is in the expansion of 1 half 3 by 2 minus half. The way in which we can get 1 half 3 by 2 minus half from this is by applying the t plus operator to this. Now what I'm going to do is apply the t plus operator to both sides of this equation. On this side I'm going to apply t plus as it stands. On the right hand side I'm going to apply its equivalent operator t1 plus t2 plus. Now on the left hand side, applying t plus increases the T3 eigenvalue from minus 3 by 2 to minus half, and it produces an extra factor in front, which is basically 3 by 2 minus 3 by 2. That's the root over j minus m factor, and then you have a j plus m plus 1 factor, 3 by 2 plus minus 3 by 2 plus 1. The second factor, of course, is just 1, and the first factor works out to be square root of 3. So, basically, t plus acting on this gives you root over 3, 1 half, 3 by 2 minus half. Similarly, t plus 1 acting on this will just increase this minus 1 to 0 with an extra factor of root 2, and t plus 2 will increase this minus half to plus half with a factor of 1. So, what this gives us is root over 3 times this particular total isospin eigenstate with capital T of 3 by 2 and small t of minus half, small t3 of minus half, is equal to root 2 times this state, where these are of course t1, in this case T for the pion, T3 1, T2 T2's third component. And similarly another factor like this, and this helps us identify the Clebsch-Gordon coefficients that we get when we add an isospin 1 with an isospin half. If you are going to look at the 3 by 2 minus half result for the total isospin and total isospin's third component, the 0 minus half piece is the one which comes from 0 and minus half T3 values for the individual particles, and that's root over 2 by 3. This root 2 divided by this root 3. Similarly, the other Clebsch-Gordon coefficient that you can read off directly from here is C1 half, again spin 1 being added to spin half, or really isospin 1 being added to isospin half, leading to total isospin of 3 by 2 and total isospin's third component minus half, but the contribution coming from minus half and plus half, minus 1 and plus half for the T3 eigenvalues for the individual particles, and that's root over 1 by 3. Now the other expansion that we are going to need is for the orthogonal state 1 half, half minus half. Note that's the one which is going to be relevant for the other possibility when you add a spin half to a spin 1, and it will be relevant for these two cases. Now we can easily figure that out by noting that this state and this state correspond to different values for the total isospin quantum number, and therefore they must be orthogonal to each other, but being states with T3 eigenvalue equal to minus half, there must be linear combinations of these two states. And orthogonalizing this with this immediately gives us that the coefficients must be root over 1 by 3 and minus root over 2 by 3. Now there is a sign convention which can be used here to decide whether this one will be plus 1 by root 3 and this one will be minus root over 2 by 3, the case that I have written down, or whether you should have minus sign here and the plus sign here. But frankly, as you will soon see, the overall sign in this case will not really matter for our results, and they shouldn't, because after all, the overall sign is just an overall phase factor and that should not make any difference as far as the physics is concerned. So, going with this particular sign convention, the one I have just written down, the Clebsch-Gordon coefficients work out to be root over 1 by 3 and minus root over 2 by 3. Now let us try to see how we could use these values for the Clebsch-Gordon coefficients and our basic formula to figure out the scattering matrix elements, or at least relationships between the scattering matrix elements for the three different scattering processes. The first one is pi plus p to pi plus p scattering. Here you have a sum over t. I have not written down a sum over t3 because t3 of course has to be 3 by 2. Remember 1 and half basically come from pi plus and the proton. And this 1 and half are of course for the pions and the nucleons. This is the total isospin angular momentum. And what we are looking at is this factor twice, because after all pi plus p is the in state as well as the out state here, times st. Note that when you add 1 and half, the only way you can get 3 by 2 is if you have capital T equal to 3 by 2. And therefore the sum over capital T simply becomes one term, the term with capital T equal to 3 by 2, and that's simply S3 by 2 here. These two Clebsch-Gordon coefficients obviously have to be both 1. So that one was simple. What about the other possibilities? The possibilities where the inker state is pi minus p. Let's consider the case where pi minus p elastically scatter to pi minus p. So what you have once again is this formula where I have again put in the T3 total eigenvalue as minus half, which it has to be. Remember pi minus has a T3 component of minus 1 and proton has a T3 component of plus half. So this is the proton and this is the pi minus. And the two together give you a T3 value of minus half. That's the only value of T3 for which you will get a non-zero Clebsch-Gordon coefficient. So you still have to sum up over capital T, and note that because you're adding isospins 1 and half in both of these factors, of course both factors are identical again because the in state and the out state are the same, and because of this you are going to get possible T values of half and 3 by 2, and both of them are going to contribute here. For T equal to 3 by 2, what we get is this term here. Capital T has been replaced by 3 by 2. You get a square because both of these factors are of course the same. And S comes with a suffix 3 by 2, the reduced matrix element for T equal to 3 by 2. For T equal to half, you get a very similar expression except that capital T here is half. Everything else stays the same. And of course you have S half here. Now these Clebsch-Gordon coefficients have been calculated just a while ago. This one, for example, is the one which you get when you add up a spin 1 and a spin half to get total angular momentum or total isospin angular momentum in this case of 3 by 2 and total isospin momentum third component of minus half. And this one is a factor here, root over 1 by 3. The other factor, this one, is what you have here for adding up isospin 1 and isospin half to get an isospin total of half and a projection of minus half. And this is the relevant factor. Now you're going to square these two factors and then this expression becomes 1/3 S3 by 2 plus 2/3 S half. A very similar calculation can be done for the third scattering process, which is an inelastic scattering. So that's slightly different from the previous two cases. The scattering process in which pi minus p goes to pi 0 n. Here the out states correspond to pi 0 and n. It's a pion, so you have 1 for the total isospin. And it's a nucleon, so you still get a half. But because you're dealing with a pi 0, you have a third component of 0, and for the neutron, you have a third component of minus half. On the inside, the side of the in particles, you again get a pion and a nucleon, so 1.5 for the isospin total values, but minus 1 for the pi minus and plus half for the proton. And you have to sum up over all possible T values. Here again, because you're adding 1 with half, the only possible T values are 3 by 2 and a half. So you actually get two terms. The first one is for T equal to 3 by 2. I've just taken this and put down T equal to 3 by 2 everywhere. And the other term is for T equal to half. Now, the Clebsch-Gordon coefficients necessary for this have already been calculated. These are the two Clebsch-Gordon coefficients that you had for the total value of 3 by 2. So up here, these are the two corresponding Clebsch-Gordon coefficients, root over 2 by 3 and root over 1 by 3. The other term actually has Clebsch-Gordon coefficients which come from the product of these two terms, root over 1 by 3 and minus root over 2 by 3. And let me just point out that here, if you had chosen the different sign convention, this would have become minus, this would have become plus, but the overall factor would still have stayed the same, which is as we expect. So ultimately you end up with this particular scattering matrix element being root over 2 by 3 S3 by 2 minus root over 2 by 3 S half. So to summarize, what we have here is that the three scattering matrix elements can be written down entirely in terms of two reduced matrix elements S3 by 2 and S half. Now it so happens that in the region which is experimentally relevant, the scattering matrix element corresponding to S3 by 2 actually exceeds S half by a large amount in magnitude. In other words, for all practical purposes, you can ignore S half compared to S3 by 2. So this one, of course, is S3 by 2 always. This one is approximately 1/3 S3 by 2. And this one is approximately root over 2 by 3 S3 by 2. Now, once again, let me remind you that the scattering cross-section which is actually what is experimentally measurable, is proportional to the modular squared of the scattering matrix elements, and that leads to the following ratio for the three scattering processes. The cross sections for these processes are in the ratio square of 1 is to 1/3 is to root over 2 by 3, that is 9 is to 1 is to 2. Now this is for the individual scattering cross sections. If you were just interested in the total scattering cross section for protons with pi plus as opposed to protons with pi minus, what you have to do is to add up the final two scattering cross sections, because you are not really paying attention to what the final state is. You are just paying attention to the fact that a proton is scattering with pi minus. So this ratio will be 9 divided by 1 plus 2, and that is equal to 3. Now these predictions, both the ratio 9 is to 1 is to 2, and as a consequence this particular prediction, that the ratio of the number of protons which scatter of pi plus as opposed to protons which scatter of pi minus under identical other conditions is just 3 is to 1. These are experimentally verifiable predictions, and they are actually borne out rather well by experiments. Now, as we had explained at the beginning of this video and also at the end of the last video, this particular section is a bit of an outlier because we are going and explaining stuff which Weinberg does not really talk about. But I still thought that this is an important enough result and with enough real life applications for us to worry about. In the next lecture, I am going to return to what Weinberg talks about next, which is the effect of discrete symmetries like parity and time reversal on scattering matrix elements. Bye till then.